In this lecture, we will be covering arc length of space curves. Recall the definition of a parametric curve in R3, three-dimensional real space, is a triplet of functions x equals f of t, y equals g of t, z equals h of t, that give x, y, and z coordinates as continuous functions of t for t in some interval. We call the x equals f of t, y equals g of t, and z equals h of t parametric equations. Further, we define the position vector for this curve C as the vector r of t, where it has these f, g, and h functions as components of the vector. And we say C is a smooth curve if the components f, g, and h all have derivatives which are continuous. For such a curve, we want to introduce the concept of arc length. So let's consider that type of smooth curve that we had just discussed in the previous slide in three-dimensional space, depicted here. And we want to calculate the arc length of this curve. So let's run the clock for the parameter from time A to time B. And let's think about what the curve looks like during that time. And we're going to assume that during that interval of time, this curve is traced out exactly once. And we want to know the length of this curve between time A and time B. One way you can think of this intuitively is think of this like a roller coaster. So if you have this roller coaster, we want to know how long the actual tracks are. If you put an odometer on the roller coaster, what would it read on the roller coaster car when it leaves at, say, the beginning of the ride at time A, and when it ends at time B. Now, the approach that we take to calculate this arc length is an approach we're used to, where we first partition the interval of time. So we partition the time interval AB using, say, A is T0 less than T1 less than T2 up to Tn, which will be B. And we set up a regular partition so that our delta Tk, which is the difference between Tk and Tk minus 1, will just be B minus A over N. So we are partitioning AB into subintervals of equal length. For each one of these times in our partition, we'll think of Tk in general. These will give us points on our curve. And let's think of one piece associated with time Tk minus 1 to time Tk. And we're going to concentrate on finding an approximation to the arc length on this piece. And we're going to call this arc length Lk. So Lk will be the arc length of the curve over that subinterval, time Tk minus 1 to time Tk. And we will approximate the length of this curve using a line. So we will connect these 2 points on the curve with a line segment, and we want to find the length of that line segment. And the way that we do that is by thinking about position vectors. So we know that this first point has the position vector r of t k minus 1, and this other point has position vector r of tk. And using our triangle laws for vector addition and subtraction, we know that the length of this line segment is nothing more than the difference between these 2 vectors in magnitude. So the length of that line, let's call that, say, little lk, is equal to the magnitude of this vector. And we're using this to approximate this piece of the curve, lk. Now the idea of this doesn't look like a great approximation the way we've drawn it, but think about the idea of refining this partition and getting more and more points along this curve, and you get more and more of these line segments, and the summation of all these line segments will get, the length of these line segments will get closer and closer to the actual length of the curve. So we have this expression, but now note that we can multiply and divide both sides by delta t. We can then bring this delta t in the denominator into the vector magnitude, and so we get r tk minus r tk minus 1 over delta t times delta t. And we now note that this expression here gives us the length of this line segment, little lk. And remember, we are using that to approximate the arc length of this curve, capital LK. We now do this for each piece of the curve. And so we're going to have n of these. And the idea is the overall length of the curve, which we call L, is equal to the sum of each of these curve pieces, the lengths of these curve pieces, and each of these curve pieces has a length that's approximated by this. And so that gives us this expression here. So the overall length of the curve is the sum of the lengths of the individual pieces, and each one of those is approximated by this expression here. And we note that this inside the length calculation is what we call the difference quotient of the vector r of t. Thus, by definition, if we let delta t go to 0, let's think about first what happens graphically. As we mentioned, you get more and more of these points, and you get more and more of these line segments. But in this piecewise linear way, the line segments collectively will look more and more like the curve, and when you let delta t go to 0, it will actually become the curve. And mathematically, this expression becomes the derivative, straight from the definition of derivative for a vector-valued function rt. And so when we let delta t go to 0, this arc length approximation becomes inequality, and we have the integral from a to b of the magnitude of r prime of t dt. And we state this result here. The arc length of a smooth curve, r of t, as before, for t between a and b, that is traced exactly once as t increases from a to b, is given here. And you see the way we've written this, this is an expression for the magnitude of r prime of t. And recall that r prime of t, when we think of r as a position vector, r prime of t we call the velocity vector. So you can think of this as integrating the magnitude of the velocity vector to get arc length. Let's see an example. So recall this example that we've seen a few times now. We have r of t is cosine of t, sine of t, and t. And we're going to find the arc length of this curve for t varying between 0 and 2 pi. And graphically, we know at time 0, we are here, and at time 2 pi, we will have gone once around. So the arc length that we will be finding will be for one piece of the curve as depicted here. And to do this, we use the formula that we just derived. So the first thing we need is the velocity vector. And we differentiate by components. So the derivative of cosine of t with respect to t minus sine of t. The derivative of sine of t with respect to t is cosine of t, and the derivative of t with respect to t is 1. So this is the vector that we need. We then need its magnitude, and so we take the square root of the sum of the squares of the components, and so we'll have minus sine of t squared plus cosine of t squared plus 1 squared. And recall our classical trig identity that sine squared of t plus cosine squared of t is equal to 1. And so we see that this velocity vector magnitude is root 2. Thus, our arc length, we integrate from 0 to 2 pi, the magnitude of the velocity vector dt, which in this case is root 2. Taking an antiderivative, we have root 2 times t, and we evaluate between 0 and 2 pi, or root 2 times 2 pi minus root 2 times 0, or 2 pi root 2. And so this gives us the length of this helix from time 0 to time 2 pi. We look at another example. Suppose we want to calculate the arc length of this curve. R of t is t squared 2t natural log t for t between 1 and e. And this is a depiction of what this curve looks like. So as before, let's calculate r prime of t, also known as the velocity vector. So we have 2t, 2, and 1 over t when we take the derivatives of each component. The magnitude of this velocity vector is thus, we have 2t quantity squared plus 2 squared plus 1 over t squared. This becomes 4t squared plus 4 plus 1 over t squared. One thing to note about these types of problems is the vector valued functions you'll see will look sometimes a little unusual. And that's because you have to choose unusual functions so that the magnitude of the velocity vector works out as a square, so that it's something you can integrate. So in calculus exercises, typically you're seeing problems like this where the math works out nicely. In real life, in many of these calculations, you wouldn't actually be able to find a derivative, and you would have to use numerical integration to actually numerically approximate the length of such a curve. But in problems like this, things do factor. So this becomes the square root of, we'll see this factors as 2t plus 1 over t quantity squared. And so we can check this. Square 2t, you get 4t squared. Square 1 over t, you get 1 over t squared. Multiply these two together, you get 2 times 2 is 4. So this does work, and we see this becomes 2t plus 1 over t. And now that we have the length of the velocity vector, we use our rule that the arc length was the integral from a to b of the magnitude of the velocity vector dt. And so we have this depicted here. And taking an antiderivative, we get 2t squared over 2, or t squared, plus the natural log of the absolute value of t, evaluated between 1 and e. Plugging in the upper limit, we get e squared plus natural log absolute value of e, minus, when we plug in the lower limit, 1 squared plus natural log absolute value of 1. Of course, natural log of absolute value of e is natural log of e, and we know because the natural log and the exponential are inverse functions, that's 1. And natural log absolute value of 1, that's natural log of 1, which we know is 0. Thus, this becomes e squared plus 1 minus 1, or e squared. So this gives us a couple examples of how to calculate arc length, and we're going to explore this more. In the next lecture, we talk about something called the arc length parameter, because we need to get set up for something called the TNB frame.